Okay, let's get started. So, just as a couple things, um, lab starts next week, so that's fun. There is a lab safety contract for each one of you. It's relatively straightforward. You read through the all the fun stuffs about coming to lab and being safe in lab. Sign it, date it, all that fun stuff. If you're feeling adventurous, you can do it electronically. Otherwise, print it out, bring it into lab with you next Wednesday. The other thing I just want to make mention of is that I did slightly adjust the course syllabus. I didn't change any order of things or what you need or grading or anything like that. All I did was just update, like you can see problem set number 1 is due. That's all I added. So just as an FYI, so that's been updated on Blackboard so it's more clear that, in case you, you weren't sure when something was due or you forgot, it's just, that way it's just much more clear in terms of what's due on a given basis. So but that's it. Nothing crazy. So today we're going to be diving into our first topic, and that topic is basically the topic for for the entire course. But this is just the basics, thinking about what do you need to know exactly, basically to know to progress in this course. And this is going to be looking at organic molecules and functional groups. So today's a pretty important class in terms of knowledge because it really does set the stage for the rest of the semester. So as you saw from the title screen and as you see from this slide, we're looking at organic chemistry, and the word organic is used a lot outside of science. It's also used in agriculture to thinking about organic farming. But when we think about organic in terms of science, we think about it in terms of the study of carbon. So anytime you hear organic in science, it's an organic compound. It just means it's a compound that has carbon in it. And there is an entire field of chemistry called organic chemistry. And for those of you that are going to or plan on going to med school or vet school or dental school, you have to take an entire two semester course load called organic chemistry. So it's kind of a big deal. And part of the reason why it's a big deal is because it's basically the chemistry of life. As you guys know, carbon is central to life. Life doesn't exist without carbon. Your DNA made out of carbon. Your proteins made mostly of carbon. Your cellular membranes, your cytoplasm, bacteria, the food you eat, everything is made out of carbon. So carbon is really the central molecule of, of life. So it is a particularly important thing. And it's not just, things that are involved with life. Every sort of facet of you that you do in your everyday life, food, medicine, gas, refrigeration, soaps, they're organic compounds. And this course really does explore organic chemistry from the sheer basics of it all the way up to thinking about neurons and proteins and all the fun stuff that makes life possible. And our lab is going to explore what are some of the properties of organic molecules, what are some of their even some of their smells, right? So for instance, we work with not often but a few times we work with a compound called cinnamaldehyde, and cinnamaldehyde is an organic compound. And for those of you that like cinnamon, cinnamaldehyde is simply the carbon compound that gives cinnamon its smell. So organic compounds are again super duper important for you, but also just important in general for understanding the planet. And the other thing I'll just make mention of is that organic doesn't mean natural. You could, in one sense, it kind of does mean natural, right? Like proteins are natural, carbohydrates are natural, but we do know that you can synthetically produce organic compounds. Polyester and nylon are two great examples of synthetic carbon-based compounds. So that's my spiel about organic chemistry, why it's important. Organic chemistry is also not the most fun of sciences, and I don't like to sugarcoat that because it's a lot of memorization. I think I mentioned this in the first class. The first part of Intro to Chemistry is, or Principles of Chemistry, I should say, is, a lot of like problem solving and stuff like that. This is, inherently more memorization based. So just two examples here of some organic compounds. We've talked about methane quite a bit in Principles of Chemistry 1, and this is methane, CH4. It's a greenhouse gas. It's the primary component of cow burps. It's produced naturally. It's also natural gas. So it's our friend methane. Then we have ethanol. So those of you that well, most of you aren't old enough to like these things, but for those of you that are old enough, ethanol is what's present in alcoholic beverages, so which makes beer and wine and all those other drinks oh so fun. It's also what's present mostly in hand sanitizer, so just as a note. Now, we can also look at some much larger and more complex organic compounds, such as capsaicin. So for those of you that like spicy food, like myself, I like spicy food, but not like Jamaican people like spicy food. Like they're crazy with their spicy food. That stuff hurts. But I like spicy food tolerably. But this is capsaicin. As you can see, it is chock full of carbons and is chock full of hydrogens and nitrogens, but it's mostly carbon. And so capsaicin, which burns your mouth, is an organic compound. This is also what's found in pepper spray, or a lot of pepper sprays, I should say. And it kind of burns. So caffeine is another fantastic example of an organic compound. Everyone runs on caffeine probably, whether it's natural caffeine from your body producing it, or if it's just you're drinking. Like for instance, I'm drinking a soda right now, has caffeine in it. So that's fun. But when we think about what actually defines an organic compound, it's anything that basically contains carbon atoms, and most organic molecules contain hydrogen atoms as well. Now, carbon is one of the best molecules to study because it's so dang simple in its behavior. Carbon is inherently not very reactive, and carbon always forms 4 covalent bonds. And carbon will never form 5. Well, there are really rare cases where carbon will form 5 or 3 or 2, but carbon always wants to fulfill its octet rule, so get 8 electrons around it by forming 4 bonds. So remember, carbon has 4 valence electrons, so it wants to naturally form 4 bonds to satisfy its octet rule, i.e. get 8 electrons in its outermost shell. Now, hydrogen is the other main component of organic compounds, and hydrogen, as you probably remember, has 1 valence electron, but its 1s orbital can only hold 2 electrons. So our friend hydrogen here only forms 1 bond. So it's kind of nice when we look at organic compounds, the 2 most common things in them, hydrogen and carbon, in terms of their bonding behavior, it's very, very simple. So it's actually kind of nice when we're thinking about these 2 compounds. Now, I mentioned carbon likes to form 4 bonds, but it doesn't always have to be 4 single bonds like we would see in something like ethane. Now, carbon commonly forms double bonds, so we see ethylene here forming, so C2H4. It's pretty common. Now, ethylene is a pretty cool compound. For those of you that like fruit, ethylene is the gaseous compound produced by fruit that ripens it. So just as a fun fact. Carbon will also form triple bonds, not that commonly, but it will form triple bonds. So that's signified by these 3 triple bonds, each bond holding 2 electrons. Now, acetylene it's not super common in nature, but it is used as a fuel. So for those of you that have ever seen people work with metal, like metalsmiths, people that craft metal into things, or jewelers in particular sometimes, they'll use acetylene torches. So they burn acetylene to create a really, really hot flame to melt metal. So just some fun facts about these 2 final things. Now, as you've probably seen thus far, I mean, we've looked at glucose several times, and glucose is a type of organic molecule. Now, some organic molecules will form chains of atoms, as we see here with propane. So for those of you that have ever cooked on a grill with propane, this is what propane looks like as a fuel. But we also see ring structures pretty commonly being formed. So in this case, we have cyclopropane. You'll notice that's the same chemical formula, it's similar name, but slightly different chemical formula. So this one is C3H8, and our friend over here on the right is C3H6. So it forms this ring structure, drops two of its hydrogens, but it's still propane in the traditional sense. And we'll talk about how to name these in a subsequent lecture. But again, propane, but it's just a cyclic form or a cycloform because it's a ringed structure. Now, as I've sort of shown you already, organic compounds don't just have to contain hydrogen and carbon. When they do just have hydrogen and carbon in them, they're called hydrocarbons. Those are the easiest types of organic molecules to understand. But any type of atom that is not just found with carbon and hydrogen in it is called what we call a heteroatom. And every heteroatom will form essentially the characteristic number of bonds that we discussed last semester, but we'll go through again. And it's simply determined by its location on the periodic table. So the most common heteroatoms we find in organic molecules include nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, or iodine, if you want to go that route. And many of these also have non-bonding, i.e. lone pairs of electrons, so that each atom is essentially surrounded by its octet of electrons, right? Now that's the dream of every atom, right? Is to satisfy that octet rule. So, and remember the way we determine the number of number of bonds that are present, or the capacity to, right? It's the number of bonds plus the number of lone pairs should equal 4. So let's take a peek at these common additives to organic compounds. So we have hydrogen, which we know forms one bond and has no unbonded pair, so no lone pairs of electrons. Carbon, our friend, 4 bonds, no unbonded, so no lone pairs of electrons. Our friend nitrogen here likes to form 3 bonds, and there's typically 1 unbonded pair of lone electrons here. Oxygen, typically speaking, it likes to form 2 bonds, has 2 unbonded pairs, as we can see here. And then our halogens, whether it's fluorine, chlorine, bromine, and iodine, so the far right of the periodic table before we get to those noble gases on the right side, they like to form 1 bond and have 3 pairs of electrons hanging off them as well. But ultimately, these are behaving in the same way they behaved in Principles of Chemistry 1, right? They say, how many electrons do I need to fill my outer shell? That amount is dictates how many bonds that they will essentially form, which is nice. Now, the most common multiple bond between a carbon and any other heteroatom is going to be the carbon-oxygen double bond. Now, we see this pretty commonly. So, for instance, we have methanol here, CH3OH. So, methanol is, it's a solvent. It's commonly used in industrial processes. It smells really bad. You guys will see it during the semester. But methanol is an alcohol, as you can see by its OL. And you see that carbon single bond binds to that oxygen, which then single binds to a hydrogen, thus fulfilling all the 8 electrons each need, and the 2 electrons each hydrogen needs. Now we have formaldehyde here on the right, so CH2O, and formaldehyde is a preservative. This is one of the things they pump in cadavers and people that are have recently passed away to preserve them. It's a really great preservative. Toxic in high amounts. If you just drank a cup of it, you'd be fine. But if you drank like a half a gallon of it, you'd get sick and die. Also, really, as we sort of discussed, well, actually, if you took Biology 1, when you talk about metabolism, formaldehyde's a pretty common byproduct of metabolism, just as a note. But anyways, that's formaldehyde, carbon double bonded to oxygen. So typically you'll see oxygen bound to carbon either once or twice, with this one being likely the most common, with this one being present but not as common as the single bond. So those are our heteroatoms. Those are the basics. So we're going to dive into a relatively new topic. We talked a bit about the shape of molecules in Principles of Chemistry 1, but we didn't dive too much into it. So to get a little bit more in depth into it, we're going to talk about the VSEPR theory, or the VSEPR theory, which is called VSEPR. And so This tells us that the most stable arrangement keeps the groups on a central atom as far away from each other as physically possible. And why is that, you might ask? Well, the reality is it's just about those electrons, right? Electrons are repulsive to one another. So if two electrons come together, they bound off one another. So by keeping the atoms as far apart as you physically can, it keeps the electrons from interacting, thus making it the most stable. So typically speaking, when an atom is surrounded by two groups, it forms a linear formation and thus has a bond angle of 180 degrees. So we have an atom here and an atom here. They're each bound twice, so it's this carbon's bound to this carbon and this hydrogen and vice versa here. Because they're only bound to two things, they will form a linear structure, thus the angle between this and this is 180 degrees, so it's just completely flat. And it's the same thing for the other carbon here. Fun stuff. And then we can visualize this with, like a ball and stick model, and it looks very much like this. So similar things. Now, an atom surrounded by three groups is what we call trigonal planar, and it has a bond angle of 120 degrees. So when we look at our friend ethylene here, we have two carbons, each bound to three distinct groups. And as you can see, the angle between this hydrogen and the carbon here is 120, 120, and 120. And then finally, any atom that's surrounded by four groups is what we call tetrahedral, and these have bond angles of exactly 109.5. Now, this is organic chemistry, and there's a limited number of stuff that binds to organic molecules. So these are the three shapes we're thinking of primarily in this class. But I will say there are some atoms that will bind to 6 and 7 things, and they start to take much different shapes. But for the purpose of this class, we're just thinking about these three distinct shapes of molecules. So we have linear, we have trigonal planar, and we have tetrahedral. So nothing crazy, but again, distinct shapes. Now, when we're thinking about how to draw this 3D shape, and a lot of organic chemistry is understanding 3D structures, and you might think, why do I give a dang about 3D structures? Well, the reality is structure, and this is a matter of it's biology or chemistry, structure really dictates the function of molecules. If you don't remember anything from biology or chemistry 1, I do hope you remember that. Structure and function are linked together. They're best friends. So for instance, this behaves very differently than this, and that's due to the shape of the molecules. So just remember that shape dictates function, right? So you can think about like like when you're a little kid, right, and you're playing with those those little wood blocks and trying to put the blocks in the holes, right? You can't put a square block into a triangular hole, right? Because the shape is wrong. And that's the same thing with the shape of any chemical or any biological entity for that matter. So, but how do we physically draw these atoms in 3D shape, right? We can do, this is fine and this is easy to draw, right? But how do we draw, a tetrahedron? Well, we do know that when we draw tetrahedrons, a solid line always dictates bonds that are within the plane. So like when you're looking at the paper, it's up, down, left, right? Think about it like a compass on the paper. So that's what we mean by in plane. Now a wedge, just a solid line here, is basically it's coming out towards you. If you think of, again, thinking about it on a flat piece of paper, it's coming out towards you. And that's in contrast to our dashed line, which basically says that molecule is going through the paper out the back. So we can represent 3D drawings without having to just try to draw something in 3D simply by using the bold to come at you, the dash, the solid line here to be in plane, and then the dashed line to go directly behind the molecule. So just as a thing, this is an important thing to keep in mind, simply because you're going to be drawing quite a bit, whether it's in lab or whether it's in lecture. Organic chemistry is all about drawing stuff and naming stuff. So remember this. This is like probably the most important thing I'll teach you in this entire class today, is just how to draw things. Because again, you're gonna do this on your homework. You're gonna do this in your problem sets. You're gonna do this on, well, you're not gonna do that on exams, but you have to recognize it on exams. So remember this. Very important slide, number 14. Now, nitrogen is a special case here. Nitrogen likes to bind to 3 atoms. As we discussed, remember nitrogen has 5 valence electrons, so it likes to bind 3 times to get to that magic number of 8. Now, nitrogen, when it's bound to 3 things, has a lone pair of electrons, and so when we're drawing nitrogen does take a trigonal pyramid shape where the carbon comes off one side and the hydrogens come in plane as well as towards you. And then we have the lone pair actually physically giving it shape as well. So it is that pyramid shape as well. So just as a note, just because something doesn't have some 4 things bound to it doesn't mean it's not taking that trigonal planar shape, and it's taking that pyramidal shape, just as a note. Oxygen does the same thing. So when oxygen has 2 lone pairs of electrons, they basically act as 2 additional electrons, giving it a distinct shape as well. Now, when oxygen is attached to 2 atoms and 2 lone pairs, it makes a bent shape, where we have, again, thinking about this pyramidal shape here, it's bound to the carbon, oxygen, hydrogen, right? And the 2 atoms essentially act as a, like you can think of it almost like additional molecules present, giving a distinct bent shape when oxygen is bound twice. So 109 degrees. So 112, 109, and just to reiterate, 120 for 3, 109.5 for 4 things, and 180 when it's just 2 things. And this is just I probably should have just gone to this table. This is a handy dandy table. When you take your exam, I think this is be a pretty good table to have on your little cheat sheet. But this gives you the total number of groups, the total number of atoms, and the total number of lone pairs, and giving you the shape around that central atom and the approximate bond angle. So, again, pretty awesome table, if I do say so myself. Not like I created it, but like, it's a pretty awesome table. So, let's talk about drawing them. So we talked about 3D shapes. How do we draw structures? Well, we can do a couple different things to represent organic molecules. So the first we can do is what we call a condensed structure, where all of the atoms are drawn in, but the 2 electron bond lines and the lone pairs on the heteroatoms are generally omitted. In terms of not being able to hear things, in terms of Blackboard, it's usually your internet is like tripped up, just as a note, Hawa. Now, so in terms of, let me get back to where I was. So in this condensed structure where we have all the atoms are drawn in, but the 2 electron bond lines and the lone pairs are generally omitted. So this is the, thinking about what we have here, this generalized structure. We can do a condensed structure by simply omitting all the bonds. And this is functionally equivalent to this. Because again, CH3, CH3, CH2, CH2. So this and this are functionally equivalent. That's okay. Again, sometimes just internet drops, and that's the first thing Blackboard decides to say. Instead of dropping video, I'm going to drop audio. I don't know why. It's stupid. So, yeah. So this is our condensed structure. We could take this compound and draw in a condensed form, but you'll know it keeps the same order, right? CH3, CH2, CH2, CH3, and that's the same order. Now, if I flip things around, it's not the same structure, right? So if I pretend I went CH3, CH3, CH2, CH2, that's not the same structure. I've completely changed my structure by doing that. Go to the next slide. Now, commonly, what we will see is when we're drawing a condensed structure, some bond lines will be physically drawn in for effect to show a specific pattern of bonding. So we have this molecule here, CH3, CH, so on and so forth. And there's a special, what we call a methyl group, CH3, bound to the second carbon. Now, we wanted to note that in a condensed structure. We don't want to think that we wouldn't write CH3, CH, CH3, thinking it's all a linear structure. So we denote that there's this branch coming off by having this vertical line come off the fact. So this, again, this and this are functionally equivalent, and we have this little vertical bond to denote that this methyl group, again, the CH3, comes off this specific carbon. So again, condensed structures, easy to draw. This is much faster to draw out than this. I guess technically to write out, but it's technically easier to draw out too. And we can actually take a condensed structure and make it even more condensed. So, you know, just making things easier to draw. Now, if we have this molecule here, so CH3, CH2, CH2, CH3, we can take this two CH2s and condense it even further. So we would just write CH2 with the subscript 2. Now, you should recall that subscripts on anything, whether it's an atom or a molecule, like here, or I should say on parentheses here, tells you that you have 2 of those as well. So in this case, we're taking these 2 CH2s and compressing them into CH2 subscript 2. Conversely, if we have this structure here, where we have 2 CH3s bound to this one carbon here, we can condense those as well without the vertical line by simply writing CH3 followed by CH. So we know that this CH is in turn bound to 2 of these CH3s. So nothing groundbreaking, but basic ways for drawing organic compounds. So we'll do a quick problem. So we're going to convert each of these 2 compounds into a condensed structure. Fun stuff. Not hard, but fun stuff. Right? So little thing fell off. So we have, you know, a string of carbons here, and we have 2 CH3 groups hanging off these 2 in particular carbons. So we want to make sure we represent these 2 CH3s on these carbons. So we start to condense things. We have CH3, CH, and we make sure we have a line coming off that C to denote there's a CH3 group coming off. Another CH, 2. And then we have that other C with another CH3 coming off it, so we denote it by there. And then we just finish it with a CH3 as well. So that's fun. Now we can further simplify this condensed structure. Now I will say, if you stopped here, that's a-okay. There's nothing wrong with stopping here. This is all functionally equivalent, right? But if I asked you to draw a condensed structure of this, this would be the bare minimum that you would have to show me. This is like the ultimate simplified form, but this is the least amount of work you'd have to do. But we can condense it even further because we see this carbon here. It has 2 CH3s bound to it, so we can do CH3 And then we know this carbon here also has 2 CH3s bound to it, so we do CH3 here as well. So simplifying stuff. But again, remember, these are all functionally equivalent, and you could go backwards, right? I could ask you to expand from here, knowing that you could go from here to here and then to here, or from here directly to here. So that's the first one. Let's look at the second one. We have this compound here, CH3, CH2, CH2, oxygen, C, and then a C bound to a chlorine. We condense it. Now we have a CH3, which we see here, 2 CH2s, which we see here as well. We see an oxygen. We don't have to denote the lone pairs at all. Those are implied, right? Unless we put a charge on the oxygen, it's implied that it has its lone pairs. We have a CH2, which is then bound to a chlorine. Now, because we have 2 CH2s back to back, as we discussed, we can simplify that by writing CH2 subscript 2. So, remember, all functionally equivalent, all tell you the exact same thing about the structure, but just a simplified way of writing things. Again, this is much faster to write out than this would be. This is probably easier to understand in terms of structure and all that fun stuff, but you know, this is, again, much faster to write out. So that's simplified condensed structures. Now let's talk about what we call as a skeletal structure. Now you might have seen these before, but we're going to dive into exactly what they mean. Now for a skeletal structure, and I'm just going to jump the gun here and show you what a skeletal structure looks like. And we're going to give you the example of cyclohexane. So hexane, because there's 6 carbons bound to a bunch of hydrogens. We can see that each carbon has 2 hydrogens bonded to it. But we could take this formula and actually just simplify it very, very simply by making what's called a skeletal structure. We make the assumption that every time we have a little peak here around this hexagonal ring, that's going to be a carbon, and that each carbon, unless we've denoted otherwise with a double bond or triple bond, we make the assumption that each carbon has essentially bound to 2 or more hydrogen. So in this case, we have a cyclohexane ring. There's a carbon at each one of these points, and we know, because there's no double bonds or charges or anything like that, that each carbon wants to bind 4 times. Thus, if this carbon here is bound to this carbon and this carbon, there has to be 2 hydrogens bound to this carbon as well. So again, these two are functionally equivalent, right? This apex here is equivalent to this carbon here. This one is equivalent to here, here to here, and so on and so forth. So much faster way of drawing, right? You don't have to draw all the hydrogens or carbons. You just do a bunch of lines, which is kind of nice. So back to the slide. With the skeletal structure, we always assume there's a carbon atom at a given junction of any 2 lines together or at the end of any line. We always assume, unless denoted by double bonds or other atoms present, or triple bonds even, that there are enough hydrogens around each carbon to give it 4 bonds, right? Because remember, carbon's always forming 4 bonds. And we also draw in all other heteroatoms and the hydrogens directly bound to them. So if there's an oxygen present and that oxygen is bound to a hydrogen, we always draw in that hydrogen and the oxygen as well. But we make the assumption when we draw this that is fully what we would call saturated with hydrogens. What that means is that every carbon has 4 bonds. So it's either bound to 4 other carbons or it's bound to 4 of something else. And if there's nothing else shown, it's just lines, we assume it's hydrogens. So let's look at when we have a heteroatom present. So we have cyclopentanol, so it's an alcohol, OL, and we have a ring of 5, like a house shape. It's my favorite skeletal one to draw. I like drawing the little houses. Each one you could see is bound to 2 hydrogens, except for this carbon here, which is bound to a single oxygen, and that oxygen is in turn bound to a single hydrogen. Now, to condense that, we draw a little house structure, and on this carbon here, which is equivalent to this carbon here, we attach an oxygen, and we have to denote that that hydrogen is present. So we write an OH, such as this. Because again, remember, there's a carbon here, there's a carbon here, there's a carbon here, here, and here. So that's how we do our skeletal structures. Anytime you see 2 lines coming together, they'll never be like horizontally coming at one another, right? They'll always be coming at one another at an angle. Just as a note, like you'll never, anytime you see a horizontal one, it's just 1 carbon at one end and 1 carbon at the other end. Just as a note. So, does anybody have any questions about the skeletal structures? You'll get more comfortable with them as we go through them more. As you see them more, we'll go through them again next week. Every time we see a skeletal structure for the next couple of weeks, I'm going to remind you how they work. So they'll take a little bit of time to sort of get into your brain. But again, anytime you see just lines connected to one another, it's easy. You assume that there's carbons, and those carbons are chock full of hydrogens. Again, unless I show you another heteroatom, like an oxygen or a fluorine or a chlorine or a nitrogen or something like that. So this brings us to the final topic of today's lecture, which is what we call functional groups. Now, I dropped a functional group name on you guys earlier. I said a methyl group, and a methyl group, which I told you was CH3, is simply one type of functional group. Now, a functional group, and this is a memorization part of organic chemistry, is an atom or a group of atoms with characteristics that are both chemical in nature as well as having physical properties. So a functional group itself contains a heteroatom and typically multiple bonds, a heteroatom, multiple bonds, or sometimes both together. And so we kind of look at it like this, right? We have R, and you might recognize R from protein structure. If for those of you that took biology, R groups, protein structure, they're similar. But the R in organic chemistry denotes a carbon backbone, and then we have the dashed line, obviously meaning a covalent bond, and then we have a bound to a functional group. And so the letter R in this case is used to abbreviate the carbon and hydrogen portion of our molecules. So let's talk about some functional groups. So one particular type of group that we'll discuss is what we call a hydrocarbon. Now, if we break its name down, hydro, hydrogen, not water, hydro is hydrogen, carbon, carbon. So if you put those two together, it's simply a molecule that has hydrogens and carbons together. Hydrocarbon. It's kind of simple, right? So gasoline, for example, is a hydrocarbon. Petroleum, hydrocarbon. Let me think, beeswax, hydrocarbon, right? Anything that just has hydrogens and carbons is a hydrocarbon. Now, within hydrocarbons, there's a couple different types of, essentially subclasses for these functional groups. So what we're going to be playing around with in lab next week are what we call alkanes. Now, you'll notice that this the naming convention isn't the best. I don't particularly like this naming convention, but it's alka and then NES and it's ALK, and it changes anes, enes, or ines for these functional groups. So just when you're looking at these, always pay attention to the part after the ALK part. But an alkane has only carbon-to-carbon single bonds with no functional group. Alkenes, so ENES, again, not the best naming convention, but it is what it is, have a carbon-to-carbon double bond as their functional group. Alkynes, again, not the best naming, have a carbon-to-carbon triple bond as their functional group. Alkanes, alkenes, alkynes, single, double, triple bonds. Finally, we have aromatic hydrocarbons, and these contain what we call a benzene ring. And a benzene ring is just a fancy way of saying, well, not really fancy, but it's just a way of saying a 6-membered ring with 3 double bonds. So let's look at these. Let's see what they look like together. So alkane, the most simple, we have the carbon, so the RH, bound to a hydrogen. So that's the most simple type of functional group in alkane. An example of this would be ethane, C2H6, so ethane. And this is what it looks like. There's no technical functional group here. It's just carbons bounded to hydrogens. That's all an alkane is. Now, an alkene, again, it's 2 carbons bound to one another with a double bond. And this general structure looks like this. The generalized name for this one would be ethene. Fun stuff. And it looks like this. But again, remember, its functional group is a carbon-to-carbon double bond. Alkyne, carbon-to-carbon triple bond. This is its generalized structure. Its example would be ethylene, sorry, carbon-to-carbon triple bond, such as this. And then finally, our aromatic compound. Again, it's a benzene ring, so it's a skeletal structure. Remember, each one of these peaks here, these sharp points, is a carbon, but each carbon is double bound. So that's our generalized structure, our benzene ring. So that's our aromatic. Alkane, alkene, alkyne, and then our aromatic carbon or benzene ring. Fun stuff. I don't expect you to remember these all today. You'll eventually have to start remembering them because you're gonna have to start drawing and naming, in particular, when you start to think about homeworks and stuff like that. But don't try to memorize these today. But as you see them more and more, you'll become more familiar with them, and you'll start to remember them overall. All right. Now moving into the things that are named a bit easier to disentangle. Now these are our carbon bound to some sort of hetero atom. So the first up is an alkyl halide. That's the hydrocarbon bound to a halide, right? So something that's in column 7, so far right of the periodic table. Remember, these are our halogens: fluorine, chlorine, bromine, iodine. There are other halogens, but these are the ones we think about the most. So for example, we can look at a CH3 bound to a bromine, right? So that's an alkyl halide. Now we can look at an alcohol. So this is going to be our hydrocarbon bound to an OH. So that's the characteristic of an alcohol. So ethanol, methanol, butanol, pentanol, they're all just some hydrocarbon bound to an OH group. So in this case, we have CH3OH, which is methanol. And this is the structure of methanol. But again, this is what we're typically looking at, an OH bound to a hydrocarbon. That OH group is what we call a hydroxyl group. Anytime you see OH bound to something, it's called a hydroxyl group. So this is our alcohol, right? So if you looked at ethanol, right? We looked at ethanol earlier, right? It's just 2 of these bound to an oxygen, right? Alcohols are easy to spot. Anytime you see the OH, alcohol. It's kind of nice. Now, next up is an ether, which is an oxygen in the middle of 2 hydrocarbons. So in this case, you see ROR. Remember, R stands for hydrocarbons. So it's, in this case, we see CH3, O, CH3. This is an ether group, and this will be its 3D structure. Its generalized functional group is called an alkoxy group. I think that's how you say it. Alkoxy group, alkoxy, I don't know. Pretty sure that's how you say it. Next up, again, another easy one to spot is an amine group. So those of you that know amino acids, it gets its amine from amine groups. Anytime you hear amine, it's always nitrogen. Always, always nitrogen. Amine, nitrogen. Amine, nitrogen. Always remember that. If you hear amine, you know there's nitrogen present. So there's a couple different ways we look at this. So it's the R group bound to an NH3. So that's one way we can write it. Or we write it as R2NH, or we write it as R3N. So there is 3 distinct types of amino groups that we can see. But again, anytime you see nitrogen in the group, it's always an amino group. So we can look at an example here. We have CH3 bound to NH2. And again, the characteristic of this group is some nitrogen, whether it's bound to it's NH2, NH, or just simply N. That's our functional group. And then finally, we have, again, another easy one to spot. It's a thiol group. And a thiol group is designated with the hydrocarbon R bound to a SH, so a sulfur bound to a hydrogen. Again, pretty easy to spot. Sulfur, in this case, we have CH3 bound to an SH. This is its structure, and it's called a sulfohydryl group. So lots of them are pretty easy to spot. Alcohol is classic by OH, an alkyl halide, classic with one of our halogens. Amine, classic with the nitrogen. A thiol, classic with the sulfur. The ether ones can be kind of pain in the butt to spot sometimes, but most of these functional groups are pretty easy to pick out, I guess, of a lineup, if you're looking at it that way. So let's look at some groups. So we have an ether group here. We have diethyl ether. So we see the ether here because it's an oxygen in the center with 2 hydrocarbons on either side. Remember, it's a hydrocarbon because it's a hydrogen and a carbon and nothing else. So diethyl, why is it diethyl? Well, we have 2 ethyl groups here. You'll learn these naming soon. But we have ethyl, ethyl, so it's diethyl, and then we have in the middle, it's diethyl ether. Next up, we have this monster. It's called, sorry about that, tetrahydrocannabinol. Now, this is kind of a mouthful, but you'll notice there's a couple functional groups here, actually. So I've highlighted the ether here because, again, ether bound here, right? Now, you'll also notice that there's an OH, which means there's a alcohol group here, and you can see that here, OL, oxygen, hydrogen. So Fun stuff. Now this is, for those of you that have heard of THC before, this is the structure of THC. So that's fun. So again, I don't expect you to remember all this right now, but it's something you're going to become familiar with as time goes on. And again, you'll have a cheat sheet when you do your exam. So again, strict memorization isn't going to be your best friend, but it's just simply becoming familiar with it as you do more and more problems. So next up is what we call a carbonyl group, and this is where a carbon-oxygen double bond is present. Now, for those of you that have ever seen the structure of a protein, you'll recognize this structure immediately. This is part of a structure of a protein. Carbon bound to two other things, doesn't matter what, but double bound to an oxygen that's bound to nothing else. This is our carbonyl group. For those of you that like, for instance, like soda, right? Or maybe even if you're old enough, you like beer, right? Carbonic acid has a carbonyl group in it. So just fun stuff. All right, so that's carbonyl group. Now we have a couple other groups. Again, lots of things to just remember as opposed to concepts, which again is pretty characteristic of this type of course. Next up, we have 5 more groups to take a peek at. First up is aldehyde. So we looked at formaldehyde earlier in this lecture. A formaldehyde is, an aldehyde, I should say, is distinguished by the R group. So remember that hydrocarbon bound to another carbon, and that carbon is double bound to an oxygen and a hydrogen. And this is what we are looking at for an example in the 3D structure, and the functional group is simply designated like this. A ketone is a carbon that is bound to 2 other hydrocarbons, but double bound to an oxygen with 2 lone pairs. A carboxylic acid is a carbon bound to another hydrocarbon, bound to double bound to an oxygen with 2 lone pairs, and bound to a OH group. Again, so this is distinct from, say, an alcohol, where an alcohol would just be the oxygen present, right? There would be no double bound to the oxygen here. It would just be the OH, just as a note. Next up, we have an ester, where we have carbon bound to a hydrocarbon, double bound to an oxygen. That carbon is then bound to another oxygen, which is then bound to another hydrocarbon. So getting a bit more complex. And then finally, we have an amide group, not to be confused with an amino group, which is carbon, oxygen, another hydrocarbon. Now that carbon is bound to the nitrogen. That nitrogen in turn can be bound to more hydrocarbons, so more R, or simply bound to hydrogens. Fun stuff. I know this is none of what we're talking about today is particularly exciting, but that's just the sort of the nature of this introductory class, unfortunately. So we've sort of gone through all these, but let's look a little bit more specifically. So we have an aldehyde. So this case it's acetaldehyde. This is a chemical you play with in lab this semester. Remember, an aldehyde contains a hydrogen directly bound to the carbonyl atom. So acetaldehyde, that central carbon bound to the hydrocarbon, so that's an R group, double bound to the oxygen, which is then bound to hydrogen. Now, when we take a aldehyde, we can express an aldehyde as the R group, CH3, bound to CHO or CHO. Right? So condensed structure, expanded structure. We could do the same thing with carboxylic acid. So in this case, we have an acetic acid, or that gross compound known as vinegar. Vinegar is gross. I don't care what anyone says. I think vinegar is gross. Now remember, our carboxylic acids have an OH group directly bound to the carbonyl atom. So central carbon bound to a hydrocarbon, which is then in turn bound to 2 oxygens, one of which has a hydrogen attached to it, and the other has just 2 lone pairs. Our condensed structure for this, we typically see it as that R group, so the hydrocarbon, COOH. Or, not commonly, but sometimes you'll see it written as CO2H. But again, most commonly you'll see it as CHO, COOH, like achu. Esters, same thing. Remember, esters have a OR group directly bound to the carbonyl atom. So central carbon bound to this hydrocarbon here, double bound to an oxygen. That carbon is also singly bound to an oxygen. And remember, that oxygen is then sandwiched by another hydrocarbon. Condensed structures, again, that COO, commonly what we see, but again, as opposed to what we had here, CHO or COOH, we have another piece of the hydrocarbon on the other side. Fun stuff. And we can simplify that even more with taking that COO as a CO2. Remember, these are all functionally equivalent. Condensed structures are a bit easier to write out. All right. Functional groups, not exactly the most exciting thing, right? Just lots of sort of figuring out what things look like. And you'll certainly have lots of practice in lecture and your homeworks and your labs to figure this out. So again, don't feel like you have to remember all of this today, right? You're not going to memorize all this stuff. However, in terms of, before we move on to sort of the next thing, which we talk about the properties of some of these organic compounds, we're actually going to talk about, just briefly mention that some of these functional groups give some awesome foods some of their awesome properties. So, for instance, benzylaldehyde gives cherry and almonds their distinct aroma. Isoamyl acetates give bananas their odor, which is kind of a nice odor. Not banana flavored candy, but like actual bananas. That smells really good. Citric acid, for example, gives the tartness to lemons and limes and oranges and clementines and all that fun stuff. And then ethyl butanate gives the odor of pineapples. So if you like pineapples, you owe it to ethyl butanate. So fun stuff. Now, organic compounds, and you might have picked up on this thus far because I haven't shown any ionic compounds or any other types of bonds. They're only composed of covalent bonds. So that's a nice feature of organic molecules. And they have, relatively speaking, weaker intermolecular forces. So they don't really have a lot of reactivity in terms of within themselves, like a ionic compound would. As a result of these, organic compounds have a typically lower boiling points and melting points than ionic compounds. And organic molecules themselves tend to be, not always, but tend to be, liquids or gases at room temperature. So remember, room temperature is 75 degrees Fahrenheit or 25 degrees C. And ionic compounds are typically solids at room temperature. So just some basic properties of organic molecules. Now, just because they're not ionic doesn't mean they can't be polar or nonpolar. So this this might ring a bell from last semester. We talked a bit about polarity. Now remember, all atoms, doesn't matter which one they are, they have electronegativity. What does electronegativity mean? Remember, electronegativity refers to how electron hungry they are. So remember, as you go from left to right on the periodic table, electronegativity increases. As you go from top to the bottom, electronegativity also increases. Remember, it's how badly they want to fill that outer shell. That's all electronegativity really refers to. So when we have a covalent bond that is what we would call nonpolar, it happens when two atoms that are either have identical electronegativity or very, very similar electronegativity are bound to one another. Now, two common types of nonpolar bonds that we will see in organic compounds are CC bonds and CH bonds. Those are always going to be nonpolar. Why? Because carbon and carbon obviously have the same exact electronegativity. And CH bonds have very, very similar electronegativity between the carbon and the hydrogen. So they create these non-polar bonds. Now, we have polar bonds when the electronegativity is starkly different between the two atoms. Now remember, all we really look at in organic chemistry is a very small subset of molecules. So as a general rule, if you see a carbon bound to an oxygen or a hydrogen bound to an oxygen, the electronegativity is great enough that we see a partial negative charge form on the oxygen and a partial positive charge forming on the carbon. And again, the same thing would be if there was a hydrogen bound to the oxygen as well. We see the same property as well when carbon or hydrogen is bound to nitrogen. It creates a slight negative charge on the nitrogen and a slight positive charge on the carbon or the hydrogen. And then finally, we see probably the strongest effect when the halogen, so chlorine, bromine, iodine, fluorine, is bound to a carbon. We don't really see them bound to hydrogens in a hydrocarbon. In organic compounds. But what we see is, again, partial positive charge on the carbon and a partial negative charge on the halogen. Now, why is that? Just remember, it's all, when we're thinking about covalent bonds, right, they're sharing electrons. Now, if you think about, like I'm sure you guys all played tug of war when you were kids. Think about how tug of war works, right? If you play tug of war with someone who is equally as strong as you, there's no real meaningful pull on either side, right? They might pull a little hard, you pull equally as hard back, and the rope never really moves over that center line. Now, think about tug of war if you played with a 5-year-old now, right? Pretend like you have a little brother and you two are going to play tug of war. Now, if you're going to play tug of war, you're significantly stronger than your 5-year-old. So you're just going to yank that rope away from your 5-year-old, right? That's the same thing what's happening with electronegativity. Oxygen is that big, strong older brother. Carbon is going to be the little brother. Oxygen is going to pull the electrons towards it more often than carbon will have them, thus creating oxygen to be partially, not fully negatively charged, but partially negative charged, and making carbon partially positively charged. So remember, we denote partial positive and partial negative charge with the Greek letter delta. This little weird S symbol, that's delta. So, yeah. And this is just to show you examples of organic compounds with polar and non-polar bonds. So we have ethane here. Ethane only has CC and CH bonds. Remember, these are always non-polar, thus there are no polar bonds present. That's in contrast where we have chloroethane. We have carbon. This carbon and hydrogen pair trio over here would be they would carry no positive or negative charge at all. But the CCl bond, again, the electronegativity is greater here than it is here. Again, creating a negative charge here and a positive charge here. So keep that in mind. Carbon, no positive, no charge. Carbon hydrogen, no charge. But carbon bound to oxygen, fluorine, iodine, nitrogen, there's going to be a polar bond creating that partial positive and partial negative charge. Now, there is some interesting action going on here, which we call a dipole. Now, we can look at dichloroacetylene, where we have carbon triple bonded to another carbon, but each one of those carbons is in turn bound to a chlorine. Now, because this is a non-polar bond, this is a non-polar bond, but this is a polar bond, this is a polar bond, and this triple bond is a non-polar bond. It creates two identical poles, which is kind of a weird thing to think about, right? You could think of, like, you have this weird game of 4 people tug of war. I don't know, just kind of this weird phenomena. But because the pole is equally strong on this side and equally as strong on this side, that polarity cancels out. So it creates actually a completely straight molecule, which is kind of cool. That's in contrast to when we have, say, oxygen in the center of a carbon and a hydrogen. Remember, oxygen has much higher electronegativity than hydrogen and carbon. So it creates the partial positive charge here, the positive charge here, and a net negative charge. A partial negative charge here. So the dipole, so we have two polar bonds, is pulling all towards the oxygen, which actually creates a bending shape of oxygen. For those of you that remember from the structure of water, water actually does the same thing. Right? There's two nonpolar bonds in water. That double dipole causes water to bend in this exact shape. So, fun stuff. So let's do a quick sample problem. Took this one from your textbook, just as a note. It's problem 1110. We can explain why CH2Cl2 is a polar molecule. Well, let's draw this. So we draw CH2Cl2. we draw this with the classic shape, right? Carbon in the center, bound to 2 hydrogens. There's 4 things bound to that center carbon, thus it has to be a tetrahedron shape. So coming back to the very beginning of the lecture. And we could look at the dipole here, that it's pulling away, there's nothing here, thus there has to be a net dipole pulling in this direction, right? It's sort of in between, right? Because chlorine is pulling this way, chlorine is pulling this way. When you average that pull out, it's in this direction. So not exactly the craziest thing, but just as it is. So just a couple other things as we sort of push towards the end here. Now, we have some important properties to discuss of our our organic compounds. Now, we talked about solubility in Principles of Chemistry 1, but the general rule for solubility is like dissolves like. So things that have similar properties will dissolve other things that have similar properties as well. So what does that mean in terms of hydrocarbons? Well, and what should I say, organic compounds? I don't know why I keep saying hydrocarbons in my brain. Most organic compounds are soluble, i.e. will dissolve into other organic solvents. It's pretty, right? So organic into organic. Pretty straightforward. Now, hydrocarbons and other non-polar organic compounds are completely insoluble in water. Why is that? Well, water is polar. Remember, water is very polar. So it has different properties than hydrocarbons and other non-polar organic compounds. Thus, like does not dissolve like here, right? Because they have very different properties. Now, polar organic compounds are water soluble. Typically speaking, that only occurs when they're small or contain an N or an O atom that can in turn hydrogen bond with water. So very small organic compounds like methanol will dissolve in water. But if you have a really big organic compound, it won't dissolve in water. But any organic compound that has a nitrogen or an oxygen will dissolve in water. So just some general rules. So we can just give some examples of this. We have hexane. So there's 6 carbons here. It's a small non-polar molecule, but it does not have any oxygen or nitrogen. Thus, it's insoluble in water. That's in contrast to ethanol, C2H5, bound to that oxygen and hydrogen. So that's an alcohol group. So that's a hydroxyl group. It's small. It's polar because it has a polar bond here and a polar bond here. So ethanol is water soluble. So as a general rule, if you see a polar bond, it's probably going to be water soluble. If it's pretty small, it's going to be water soluble. Now, cholesterol. This is present in the membranes of animal cells. So not in plants, but animals. There's a functional equivalent of this in plants and bacteria as well, but we're just thinking about cholesterol as in what's in animal cells. It's pretty large. It has oxygen present, but it only has 1 oxygen present. It's just a big giant mess of hydrogens and carbons. So it's too big and too many nonpolar bonds. So cholesterol itself is water insoluble. So just a sort of last part, again, because most people that come in contact with me, whether it's I'm teaching here at Fisher or I've taught elsewhere, most people are focused on health and medicine. So we'll talk about how organic chemistry fits into health and medicine. We'll pretty much do that every time we talk about organic chemistry. So vitamins are examples of organic compounds, and they're needed typically, as you guys know, in small amounts for normal cellular function. Now, the body, as a general rule, cannot synthesize most vitamins. There are some, but as a general rule, like vitamin K, most B vitamins, vitamin A, we can't get those from our own body. We have to eat them. We have to obtain them through our diet. So there are some different properties of these vitamins. There are fat-soluble vitamins that dissolves in organic solvents, but does not dissolve in water. So for example, vitamin D is a fantastic example of a fat-soluble vitamin. Vitamin D has lots and lots of nonpolar CC and CH bonds, and very, very few polar functional groups. Now, water-soluble vitamins, such as vitamin C, will dissolve completely in water, and they typically have many polar bonds. So let's look at vitamin A, because it's the first vitamin in the alphabetical order of vitamins. Vitamin A is also called retinol. It's an essential component of your vision receptors in your eyes. So if you've ever heard of people say, oh, you should eat carrots because it's good for your vision. Well, carrots are good for your vision because they have lots of vitamin A. Now, retinol is also sold as like as a skin like a skincare cream. I think it's like a prescription one. I think it's prescription. I guess it's probably prescription when it's in high quantities. But retinol, or vitamin A, helps to maintain healthy skin. In particular, it helps maintain the mucous membranes of your skin. So this is what vitamin A looks like. You'll know you see that there's an OH group here, but otherwise it's just one giant hydrocarbon. Now, it's retinol, OL. That tells you it has the OH group or the hydroxyl group. So retinol is essentially an alcohol, just as a note. So in terms of solubility, you can see that vitamin A, it's big. It basically has all nonpolar bonds. Thus, vitamin A is a fat-soluble vitamin, which is why you can apply vitamin A to your skin and it will absorb into your skin because your skin is chock full of oils. Fun fact. Now, that's in contrast to our friend vitamin C, or ascorbic acid. That's its scientific name. Now, vitamin C does a lot of different things, but vitamin C is most commonly seen as being very important for the formation of collagen. So it's one of the fibers that helps connect your skin to the rest of your body. So that's vitamin A. Its function. It does a lot of other things, but that's the most common thing it does. Now, as a note, if you get a deficiency in vitamin C, you get a disease called scurvy. So if you ever heard of, if you ever watch anything with pirates and they say, "Oh, you scurvy person," I don't know what pirates say. It's been a long time since I've watched a pirate movie. Scurvy is something that was pretty common in sailors, in particular pirates, in the 1600s and prior to that, because they actually had no access to fresh fruit while they're at sea. Now, scurvy is a cool disease. If you've never heard of scurvy before, take like 5 minutes to research what scurvy does to you. It does all sorts of cool stuff. But scurvy is a curable disease simply by eating a lemon. It's just vitamin C deficiency. So, just as a note. Now, this is what ascorbic acid looks like. You'll see that there's a ring structure here, but it's a 5-member ring. Has lots and lots of polar bonds, right? We have oxygen, 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 oxygen. Lots of polar bonds. It has lots of polar bonds, thus vitamin C is water soluble. So fun stuff. And this is just showing you your body, vitamin A, fat-soluble vitamins are readily stored in fatty tissue as well as your liver, and vitamin C are readily are soluble in your gastric juices and are readily excreted in your urine. Just as a general note about vitamins, people like to think that vitamins are, they're important, don't get me wrong, but people like to think vitamins are a catch-all for solving your health issues. Taking multivitamins and vitamins in general actually doesn't show any net benefit to your health unless you're at a deficiency. So there's been lots of research on this. So people that take multivitamins are no healthier than people that don't take multivitamins and all sorts of stuff. So just figured I'd make mention of that because people always ask me, are vitamins good for you? And I say, yeah, if you're at a deficit. So if you're at a deficit, I'm usually operating at a deficit of vitamin D just because I'm always inside and I'm pretty pale. So I take vitamin D just because I'm at a deficit. But if I wasn't at a vitamin D deficit, it wouldn't help me at all. So anyways, so that's going to be the end of today's class. Again, a lot of information, a lot of functional groups, a lot of memorization stuff. But again, you're going to become familiar with these as the semester progresses, as we go through these more and more and more and more. So don't feel like you have to absorb everything today. You're going to have a cheat sheet when you have your exam, so you're not gonna have to memorize every single thing. But again, as the semester goes, you'll become more familiar with ketones and aldehydes and ethers and all these fun things and their properties and how to spot polarity and all that fun stuff. So I'm gonna stop recording.